So let's take a look at a number of problems involving this concept of expected value. So as a refresher, for any scenario that has outcomes of A1, A2, and so on up to AI that have respective gains or losses of X1, X2, and so forth on up to Xi, the expected value for the scenario for one turn of a game or one roll of a dice or something like that, the expected value would be x1 times the probability of a1 plus x2 times the probability of a2 and so on until we get up to xi times the probability of ai. Or put another way, we simply take the expected gain or loss and multiply it times the probability of the event that would lead to that particular gain or loss, and we do that for every possible outcome or event within the scenario. So in the first problem that we're going to look at, we have a carnival game where you pick a number from 1 to 6, and then you roll 3 six-sided dice in succession. So it's like 3 separate dice rolls. If your number comes up all 3 times, you win $3. If your number comes up twice, you win $2. If it comes up once, you win $1. Otherwise, you lose $1. So what is your expected gain or loss for one turn of this game? So the first thing we need to think about are what are the different scenarios that can occur within this game, because we're going to have to figure out the probability of each. So first of all, one scenario, the best scenario if you're the player in this game, is that you have what I would say are 3 wins. You roll your number 3 separate times. Well, let's figure out what is the probability of winning all 3 times. Well, for that first roll of the die, you have a probability of 1 out of 6 of winning. You have one number that wins out of a total of 6 numbers on the dice. But you're going to win all 3 times, so you're going to roll the first one and you're going to win. And, so we're going to multiply, you're going to win on the second roll, which has a 1/6 chance of happening. All right, one winning number again out of 6 possibilities. And the third roll, you also have a 1/6 probability of winning. So all told, the probability that you're going to win on all 3 rolls is 1/6 times 1/6 times 1/6, which would give us 1 over 216. Now that, of course, that's the probability of A1. We have to multiply that eventually times the gain or loss from that situation, right? And so I usually kind of use some kind of notation like this, and I say that gains $3 according to the problem. The other scenario that could happen is that you have 2 wins, or let's go ahead and list them out. You have 1 win, or you have no wins. So we have to figure out each of these different probabilities. Well, winning twice means you're going to lose once. So let's say you win on the first roll, and you win on the second roll, but then you lose on the third roll. Now the probability of losing, if winning is 1 out of 6 probability, then a losing would be a 5 out of 6, because there's 5 numbers that are not winning numbers out of the 6 total. But then we got to take this and we got to multiply it times 3, because this losing roll could occur on the third roll or the second roll or the first roll. So basically we would have 3 versions of these fractions being multiplied just in different orders. So as kind of a short way of doing this, we can just multiply this probability times 3, which is going to give me 15 out of 216. That's the probability of winning of 2 winning rolls, rolling your picked number 2 times. And that gains us $2. Or you could have 1 win, which means you're going to have 2 losses. So you could win on the first roll and then lose on the second and lose on the third roll. And of course, that winning roll could take place in any one of the 3, so we could win in the first roll or the second or the third. So again, we got to multiply this by 3, just like we did up there. And so that's going to give me 75 over 216. And that gains me $1. The other thing that can happen is that I don't win at all. And so that's a 5. I don't win on the first roll, so that's 5 over 6. I don't win on the second roll, that's another 5 over 6. And I don't win on the third roll, that's 5 over 6. But I don't have to multiply this one times 3, because there's no other way to kind of organize or kind of arrange the 3 rolls here. It's just they're all losses. So this gives me 125 out of 216, and this loses $1 in our scenario. So now to find our expected value, we're going to take each one of these scenarios, multiply the probability of that scenario times what we stand to gain. So our 3 wins is a gain of 3 times a probability of 1 over 216, plus our 2 wins is a gain of 2 times a probability of 15 out of 216, plus our gain of $1, 1 win, is a gain of $1 times 75 out of 216, plus our loss of $1, which would be a negative 1, times a probability of 125 out of 216. Now, when you do this all on a calculator, however you're going to want to do it, I would recommend that you keep the fractions and not try and deal with decimals, because you'll get some funky decimals that you would have to end up rounding. And then when you multiply those rounded values by these gains or losses, then you end up kind of multiplying basically an inaccurate answer. So I'm going to keep them all as fractions. And when I work all this out, I end up with negative 17 out of 216. And now I'll convert that into a dollar amount, because of course in this game our gains or losses are in terms of dollars. So if I just take negative 17 divided by 216, what I get is about a loss, or negative 8 cents. I'm going to lose about 8 cents on every turn of this game. And the second problem we're looking at, it's going to actually be a little bit easier in some ways, because here we have a dairy farmer that's trying to figure out what his profit is going to be in the next year if he produces about 25,000 gallons of milk. And based on his research, he knows that the price of a gallon of milk doesn't stay constant. It's maybe going to be $1.10. It's maybe going to be 90 cents, maybe 70 cents, maybe 40 cents. These are gains, by the way, not prices. I think I might have said the price of milk. These are the gains, and so he might gain these amounts. He might break even on his milk, or there's a chance that he might actually lose money on the milk. And the probability of each one of those situations is shown down below. So if we're going to estimate the profit that he's going to make on 25,000 gallons, first we want to find what's the expected gain, or the expected value, on 1 gallon. And so I'm going to take the possible gains per gallon and multiply them by the probability of those things happening, and then add all those up. So I'm going to have, to start with, I'm going to have a gain of $1.10 being multiplied times a probability of 0.3, plus a gain of 90 cents multiplied by a probability of 0.38. And I'm just going across the table here. So a gain of 70 cents times the probability of 0.20, plus a gain of 40 cents times the probability of 0.06, plus, and I can leave this one out because if I think about it, this is a gain of 0 times the probability of 0.04. So when I just multiply 0 times the 0.04, it's just not going to matter. So I'm actually just going to skip this one. I don't have to worry about it because the gain is 0. And this last one, I have a loss of 10 cents with a probability of that happening of 0.02. Now when I multiply all these out, I'm going to get values like 0.33 plus 0.342, and I'm not rounding any of these. I want to keep these decimals if I can. Plus 0.14 plus 0.024 plus negative 0.002. And if I total all this out, what it tells me is that it's going to be about a gain of about 0.834 per gallon, right? Because this is all gains per gallon. So this farmer stands to make about a little over 83 cents per gallon. Now if I take that and multiply it times the 25,000 gallons that he expects to produce, we're going to get an answer of this farmer making a profit of, or expecting a profit of about $20,850. Now in this next problem we have a situation. This is a real life situation. Sometimes when you go to take a flight, the airline or the airport will offer you a life insurance policy. It's a $1 life insurance policy that pays out $100,000 in the event that you end up dying on the flight. So in other words, $100,000 goes to the insured person's designated kind of beneficiary, the designated recipient, if that person dies from a possible flight crash. Otherwise, the company just keeps the $1. So the records indicate that about 0.45 deaths occur per million passengers. And we want to figure out how much do they gain on one policy that they sell, and how much do they gain if they sell 100,000 of these policies in, say, a year or a month, or whatever the time period might be. So first of all, thinking back to that general idea of how we calculate expected value, we need to think about what are the two scenarios that we have to find the probability for in this case. And of course, that would be we have to find the probability that the passenger actually dies, or the probability that they don't die. So we'll say no death. Well, according to the problem, we have 0.45 per 1 million deaths, or probably 0.45 deaths per 1 million passengers. So that means that if we just express this probability as a decimal, of course, dividing by a factor of 10 just moves the decimal point to the left for each power of 10 we're dividing by. So since a million is 10 times 6, we should be able to simply move that decimal point 6 spaces to the right. So what that's going to create is a probability of 0.000000045. That's the probability that a person is going to die. In which case, right, this means a loss of $100,000 from the perspective of the airline or the airport. The probability that they're not going to die is 1 minus the probability of death, right? Those two things are complements, dying and not dying. So that would be 1 minus 0.000000045, which turns into a 0.9999955 probability. And in this case, the airline stands to gain $1. So the expected gain or loss on one policy, well, we'd have to take the loss of negative $100,000, I'm sorry, times the probability that that's going to happen, 0.0000045, and then we have to add the $1 gain times the probability of 0.9999955. And what this works out to is that this, when we multiply it out, should give us a loss of about 0.045, but this turns into a gain of practically $1, but not quite $1, 0.9999955. So what this totals out to is that per policy, the airline stands to gain, and I think it comes out to, hopefully I got my math right here, 0.954999955 per policy sold. So that's on one policy. If we would just take that and we multiply it times 100,000, we know that if this airport sells 100,000 of these policies in a certain time period, they stand to gain $95,499 and 90. Is that right? 1, 2, 3, 4, 5, 6, 900. Oh, I think I got this wrong here. Sorry, I think I wrote this out wrong. If we multiply this by 100,000, we would have $954,999.55 that they're going to gain. Oh, I just noticed that I have a little mistake here. I moved that decimal place one spot too far. So let me just move it back real quick. And actually what they stand to gain on 100,000 policies is $95,499.96 about. Sorry about that. That was incorrect.